Welcome to our final lecture, lecture 19 of number theory. And today we're going to be talking specifically about the Chinese Remainder Theorem. And this applies to systems of linear equations in one variable, mod different n's. It's called the Chinese Remainder Theorem. Apparently it's been in existence and known by some in the Chinese culture for thousands of years. Probably back in the time of the golden age of Greece. Just exactly how they came up with this knowledge, how they performed it, so forth, we don't really know, because there's really nothing that exists manuscript-wise of the accomplishments of that civilization thousands of years ago. Whatever manuscripts there were didn't survive the climate and didn't survive mass destruction by emperors who did not want these things to survive, which is unfortunate, because this gives some clue as to the sophistication of the Chinese thousands of years ago. Things that they had accomplished, things that knowledge that they had, that a lot of it vanished again because the manuscripts were on very perishable material, rice paper, and certain emperors sought to destroy anything of academic value. It was their loss, but it's our loss as well. It would be, and I'm not over-dramatizing this, but it really would be an exhilarating experience to know all of their accomplishments and how they culminated in this and other great mathematical accomplishments. Now here's what the Chinese Remainder Theorem says. Let n sub 1, n sub 2, n sub r be positive integers such that the greatest common divisor of n sub I and n sub j is equal to 1 for any pair I not equal to j. So if we take any two of these guys, they're going to be pairwise relatively prime. Having said that, the Chinese Remainder Theorem says that the system of congruences x congruent to a sub 1 mod n sub 1, x congruent to a sub 2 mod n sub 2, a congruent to a sub r mod n sub r. This system of linear congruences has a simultaneous solution, which is unique, mod n, where n is the product of all of these n sub i's. Take n sub 1, n sub 2, n sub 3, n sub r, multiply them together, and that's our n. Chinese Remainder Theorem says that if all of these n's are pairwise relatively prime, then this system of equations has a unique solution, mod n, where n is the product of all of these n sub i's. Now I will say this, there's also an algorithm to finding the solution. And what I'm going to do right now is just give the algorithm as the second part of this theorem. So our theorem continues in that we're going to give the algorithm as to how we get the solutions to this system. Here is our solution. First step, define n, and n is the product of the n sub i's, n sub 1, n sub 2, n sub r. Lowercase n is the product of n sub 1, n sub 2, dot, 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 n sub r. First step in the solution. Second step, for k equal 1, 2, 3, dot, 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 r, define capital N sub k. And capital N sub k is this number, n, divided by lowercase n sub k. Now, if we think about this for a minute, capital N sub k is the product of all of these things except the lowercase n sub k. So it's the product of all of these things except little n sub k. And we compute capital N sub k for I equal 1 through r. Next step, solve the related congruences. N sub 1, x sub 1, congruent to 1 mod n sub 1. N sub 2, x sub 2, congruent to 1 mod n sub 2. N sub r, x sub r, congruent to 1 mod n sub r. Our solution, x bar, is congruent to this number. A1, capital N sub 1, x sub 1, plus a sub 2, capital N sub 2, x sub 2, plus, dot, 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 plus a sub r, capital N sub r, x sub r. X bar is congruent to this monstrosity, mod n. And remember what little n is? It's the product of all the lowercase n sub i's. That's how we get our solution. Well, let's try an example or two. Let's try this one on for size. X is congruent to 6 mod 14. X is congruent to 3 mod 15. X is congruent to 8 mod 11. Okay. And let's identify some of the main characters here. 14 is n sub 1. 15 is n sub 2. 11 is n sub 3. And let's see, what is this? This is our a sub 1. This is our a sub 2. This is our a sub 3. Okay, we got the main characters lined up. Now let's proceed a little bit further. Okay, our first step in the algorithm, define little n, which is the product of all of the n sub i's, n sub 1 to n sub r. So that's n1, n2, n3. $14, $15, $11. And let's see, 15 times 15 is 225. So 14 times 15 would be 15 less. So I'm thinking that's 210 times 11. 10 times 210. Ooh. Let's see. 210, 210. 2310, I hope. Okay. So we have little n. Eraser. N equals 2310. And now we want to compute n sub 1, capital N sub 1, 2, excuse me, we compute our capital N sub k's, and this is just little n divided by little n sub k, or it's the product of all of the n sub i's except n sub k. So let's see, n sub 1 is going to be n over n sub 1, which is 14. That's also going to be n2 times n3. What is that? 15 times 11. 15 times 10 is 150. So one more 15 will give us 165. N sub 2, capital N sub 2, that's going to be little n over little n sub 2. In our case, it will probably be easier to compute n sub 1 times n sub 3. And n sub 1 is 14, n sub 3 is 11. 10 times 14 is 140. 11 times 14 is 140 plus 14, 154. Okay. And n sub 3, capital N sub 3, will be n over little n sub 3. By the way, if we had like 6 or 7 of these n sub i's, I might do it differently, but we're only working with 3. So I'm choosing to do it this way. Capital N sub 3 is going to be little n divided by n sub 3, which will be n sub 1 times n sub 2. And that's 14 times 15. 15 times 15 is 225. 14 times 15 will be 15 less 210. Okay, son of a gun, I think we've got it. Now let's just preserve our values. I'll write them down somewhere where I won't lose them. Okay, we tabulated our information, because if I don't, I'm going to forget it. I swear I will. We have our N1, N2, N3. I should probably put a note here that says don't erase, so I don't erase it. This is our little n, 2310. A1 is 6, A2 is 3, A3 is 8. And capital N1 and capital N2, capital N3, we have those written. Our next step, solve these related congruences. Capital N1, x of 1 is congruent to 1 mod n sub 1. Capital N sub 2, x of 2 is congruent to 1 mod x of 2. Capital N sub 3, x of 3 is congruent to 1 mod n x of 3. Capital N sub 3, x of 3 congruent to 1 mod n sub 3. Let's get cracking on the first one. Capital N sub 1, x of 1 congruent to 1 mod n sub 1. Let's see, capital N sub 1 is 165. Mod little n sub 1, that's 14. going to be able to do this unless I cut this number down to size mod 14. So I'll just use the division algorithm with 14 as the divisor. Let's see, 10 times 14 is 140, 11 times 14 is 154. That's as big as we can get. Okay. So 11 times 14. Shoot. Nuts. 11 times 14. That's going to give me 154 with a remainder of 11. Okay. So that tells me that 165 is congruent to 11 mod 14. And the congruence 165x1 congruent to 1 mod 14. Is going to be the same as 11x1 congruent, 11x1 congruent to 1 mod 14. And I have to find a solution to this. 11 mod 14 is the same as negative 3 mod 14. So I'm going to write it as negative 3x1 congruent to 1 mod 14. Oh, okay. If I let x1 be 5, I get negative 15, which is negative 1 mod 14. So what if I let x1 be negative 5? Negative 3 times negative 5 is 15, which is congruent to 1 mod 14. Ladies and gentlemen, we have our x of 1. And I'm going to have to write this down. Hold on a minute. Yeah, I'll write it down all right. As soon as I get a positive x of 1 mod 14. Forgive me, I left my brain at home today. Negative 5 is indeed a solution, but it's not a positive number. We want something between 0 and 13. So how do I get a solution to this that's positive and between 0 and 14? I just add 14, right? Negative 3, negative 5 plus 14 is 9. And is that congruent to 1? Let's see. Negative 3 times 9 is negative 27. Plus 14 is negative 13. Plus another 14 is positive 1. Yes, indeed. Okay. So this is our x of 1. And I will write that down here. Excuse me for a second. Next on the agenda, solve this congruence. N sub 2, x sub 2 congruent to 1 mod little n sub 2. capital N sub 2, that is 154. And little n sub 2, that is 15. And this one's going to be kind of easy. If we use the division algorithm on 154 with 15 as a divisor, 15 goes into 154 10 times with a remainder of 4. And that means that 154 is congruent to 15. No, it's not. Come on, Pat, get a brain. 154 is congruent to 4. Hello, the remainder, remember me? 154 is congruent to 4 mod 15. So, this congruence, n2 x sub 2, congruent to 1 mod 15 is the same as 4 x2 congruent to 1 mod 15. And this is very fortuitous. We see right away what's going to happen here. If we let x of 2 be 4, we get 16, which is congruent to 1 mod 15. Hey, so we have our x2. And this time we don't have to worry about the fact that our x2 is a negative number. Okay, we got our x2. One more congruence to solve. Okay, one more of these things to solve. Capital N3, that's 210. Mod little n3 is 11. Okay, let's see. 11 times 20, what happens there? You get 20, 20. Okay, 20 times 11 is 220. We overshot the mark. But 19 times 11 19 times 11 will be 11 less than this, which is 209. With a remainder of 1. Son of a gun. Okay. Yeah, what do we do here now? Let's see. 210 is congruent to 1 mod 11. Whoa, this is, okay. This is going to be a lot easier than I thought. This becomes 1 x x3 congruent to 1 mod 11 x3 is congruent to 1 mod 11. Okay. Just let x3 equal 1 here. Son of a gun. Now let's see, what do we have to do? We have to compute our x bar, don't we? Well, here's our solution, x bar mod n. I'm not a complete coward, but I'm definitely not brave enough to wade through this without some help. X bar is equal to a sub 1 is 6, n sub 1, 165, x sub 1 is 9, plus a2 is 3, n sub 2, 154, x sub 2 is 4, plus a sub 3 is 8, n sub 3 is 210, and x sub 3 is 1. And I'm not going to apologize. There's no way in the world that I'm going to do this without a calculator. I just did it a few minutes ago, and it was 12,438. So this is our x bar. Our solution is x bar mod n. X bar 12,438 mod, mod n. X bar mod n, and n was 2310. Okay. Holy moly. Well, let's see. I did this out also. 12,438 is equal to, is that 5 maybe? 5 times 2,310 plus a remainder of 888. So x bar is congruent to 888 mod n, and that is our solution. So that shows how we do one of the Chinese remainder theorem problems. All of them follow the same algorithm, and I would not suggest memorizing all of the steps of the algorithm. What I would suggest is just have steps 1, 2, 3, 4 written out explicitly. Just use that as your guide. Write out steps 1, 2, 3, 4, and use that as your guide as you work